now that I've introduced some of the topics, the basic topics that form the foundation of our study of dynamics, I want to talk about a general procedure that we can use for solving dynamic problems. And this will kind of lead us into some of the more specific cases and specific tools that we'll develop over the next few videos. So this general procedure follows a very similar process to pretty much anything that we would use when we're solving engineering problems. And to start with, what we would look at is just examining the system, trying to figure out what is actually going on. So we want to identify the objects involved and try to classify them in our heads as being of a particle nature or of a rigid body nature. And I've kind of talked about this in previous videos, but the basic idea is that a particle really only has translation as a possibility and not rotation. It doesn't have geometry that would indicate that rotation is a necessary consideration. Rigid bodies, on the other hand, we would be considering both the translation and the rotation as potential things that could be happening. So once we've kind of classified our things that we need to think about, we want to also identify points of interest. So this could be locations where forces are applied. It could be locations about which, or lines of action about which things are going to be rotating, so rotation centers and things like that. It could be locations on the object that are of interest because it's an output. Maybe we're talking about the scoop on an end loader and we want to know how fast that's moving, and therefore we want to identify specifically that we care about that location. I've already kind of alluded to this, but we need to understand the types of motion involved, whether we're talking about translation, rotation, both at the same time, and whether we're talking about motion in 1 dimension, 2 dimensions, or 3 dimensions, and how many factors that brings in to our analysis. The next step would be to draw free body diagrams, and this is with the purpose of identifying those forces that are acting on our particle or our rigid body. So we want to identify all those things, separate our rigid body from everything else so that we can remove, contacts with other objects, contacts with the ground, things like that. At the same time, we want to draw our kinematic diagrams. And kinematic diagrams, again, identify or graphically represent what types of motion are possible. And those could include translations, of course, which are represented as accelerations, and they can include rotations, which are represented as rotational accelerations. We can take those two things then, the free body diagram and the kinematic diagram, and set those equal to each other. Remember that those diagrams are graphical representations of our equations of motion. Once we do that, we can start counting unknowns. So we can go to our free body diagram and say, okay, maybe we know this force, we know the weight, but we don't know the reaction forces N1 and N2 in this case up here. So I want to start figuring out how many unknowns I have, because that's going to spell out how many equations we need. Of course, to be able to solve a problem in this sense, we need to have an equal number of equations for our unknowns. We can then write out those equations using our equations of motion from Newton's second law. We can sum our forces, we can sum our moments, and we can basically now mathematically represent those free body diagram and kinematic diagram pairs. We can bring in additional equations from our understanding of dependent and relative motion. So sometimes dependent and relative motion introduces additional relationships between various objects. So if I have an object which is connected to another object by a rope, that might be some relationship there, right? One influences the other. And really what that's actually doing for us is it's eliminating unknowns by adding additional equations which give us more information. So once we've got this all figured out, how many unknowns we're trying to solve for, how many equations we need, and we've identified those appropriate equations, we can solve for them, right? So we solve for our unknowns by plugging them in, some sort of brute force method, maybe just with calculation, using various numerical tools that might be available to us depending on how complicated the system is, but we solve for those unknown values. And lastly, the thing that I think we want to be careful not to neglect is kind of a sanity check. Do our results, once we've solved for these unknowns, do they make sense, right? And what I mean by that is, are the numbers in the range of possibility, right? If I'm solving a problem involving throwing a baseball and I determine that the baseball is traveling at 1,000 miles per hour, that might be problematic, right? We might want to double check our numbers, make sure our units are correct, make sure we haven't made a mistake somewhere, because it's probably unlikely, right, that we're throwing this baseball at 1,000 miles an hour. So we want to kind of just take a step back, holistically evaluate the problem and say, do these numbers relate to reality in any way? And can we kind of justify that the range of values that we ended up with is correct? All right, so in the following videos, we will be uh, looking at some more specific cases. We will be developing some additional tools that we can use and understandings that we can use to continue solving dynamic problems. All right, thank you.